Vaishnavi. Today, I will be presenting you a project which is named as Forest Cover Type Classification. So, this project focuses on building an end-to-end machine learning pipeline to predict forest cover types using cartographic and environmental features. Basically, it is a multi-class classification problem with 7 different forest cover classes, and the dataset represents a real-world geographical data collected from the forest areas. So, let's have a look at the objective. So, the main objective of this project is to accurately predict the forest cover type of a land area based on environmental and geographical features such as elevation, slope, distance to water bodies, roads, and soil type. The key challenges in this problem includes handling a large scale data, managing class imbalancing, and ensuring balanced performance across all classes, not just overall accuracy. Let's look into the dataset. The dataset used in this project comes from a UCI machine learning repository known as Forest Cover Type Dataset. It contains approximately 580,000 samples, each representing a 30 by 30-meter area of a forest land. Here is the outcome. The target variable is cover type, which has 7 distinct classes. In the dataset, you can find two different kind of features. One is the numerical, which can be seen in the elevation and distances, as well as the categorical features such as wilderness, area, and soil type. An important advantage of this dataset is that it has no missing values, which simplifies the pre-processing for us. Now let's have a look at the code. I'll start by importing all the libraries I need for this project. Currently, I'm using the pandas and numpys for data handling, matplotlib and seaborn for the visualization, and further we will be using scikit-learn for evaluation and random forest, LightGBM for gradient boosting, and Optuna for hyperparameter tuning. Basically, this cell just sets the environment for the entire workflow. Here, I'm loading the forest cover type dataset into the pandas data frame. After loading it, it displays the first 5 rows just to visually confirm that the data has been read correctly and to get a sense of what the features look like. In the next cells, we'll be checking the shape of the dataset and the type of each column. This helps me understand how large the dataset is, whether the features are numerical or the categorical. I also confirm here that there are no missing values, which means that we don't need to perform imputation, which is like replacing the missing values with either mean, median, or any kind of values. You can see that there are no null values, so there is no need for the imputation. And next, one more important step was target variable distribution. Here I am analyzing the distribution of the target variable, which is the cover type. This bar plot shows how many samples belong to each forest cover class. From the graph, we can clearly see that the dataset is imbalanced. Some classes are appeared much more frequent than the others. Because of the imbalance, accuracy alone wouldn't be reliable metric, which is why we will be later focusing on macro F1 score. In this step, I'm grouping features conceptually through like elevation, slope, distance features, hill shade values in the soil, and wilderness indicators. This helps us understand what kind of information the model is learning from and also guides feature engineering decisions later. With the help of a correlation matrix, we'll be identifying the relationship between the numerical features. Highly correlated features may be redundant. So, while meaningful correlations can inspire interactions or polynomial features. And here is the heat map, which is used to visualize the correlation between the numerical features. The stronger correlations are highlighted here. So from the correlation analysis, here are the few observations. There are the strong correlation between the related distance based features. Elevation relation features show notable interactions with other variables. Some shade variables are correlated, suggesting possible aggregations. This graph shows the distribution of elevation values in the dataset. We can see that the elevation is not uniformly distributed. Most data points fall within a very specific elevation range with fewer sample at the very lower or very high altitudes. This makes sense geographically because forest cover types tends to occur within a certain elevation bands. This observation later motivated me to create a elevation bin so that the model can learn altitude ranges more efficiently. And next one is the slope distribution. Most areas have relatively low moderate slopes, while steep slopes are much less common. This skewed pattern suggests that the slope alone might not be sufficient, which is why we will be later combining the slope with the elevation through interaction features. Horizontal distance to hydrology. This graph represents the horizontal distance to nearby water bodies. We can see that the strong right skewed distribution, meaning many locations are close to the water while some are very far. Because of this skewness, we'll be later applying log transformations to distance based features to reduce the effect of extreme values and improve model training. So, in the feature engineering rationale, we'll be seeing interaction features, aggregated features, distance based transformations, nonlinear transformations to handle skewness, bind features to capture nonlinear effects. And next comes the train, test, and split. Here, I split the data into training and testing sets. I use a stratified split so that all seven forest cover classes are proportionally represented in both sets, which is especially important for imbalanced data. Next would be baseline light GBM model. This is my baseline model using light GBM with default parameters. Light GBM is a very efficient for large tabular data set, so it's a good starting point. I also used balanced class weights to reduce the impact of class imbalance. So the baseline model is trained using the default parameters. Its main objective is it is used for multi-class classification. In this cell, I evaluate the baseline light GBM model. I calculate macro, micro, recall, and F1 scores. Macro F1 is especially important here because it treats all classes equally regardless of the frequencies. Here you can find the table of the classification report. And the next step would be hyperparameter tuning the cross validation. In this step, we'll be optimizing the light GBM model using to improve performance beyond the baseline. We have used the stratified k-fold cross validation to obtain a robust estimate of generalization performance. Here I have defined the objective function for the Optuna. This function trains a light GBM model with a specific set of hyperparameters and returns the macro F1 score. Optuna will repeatedly call this function with different parameters combination. When it comes to running hyperparameter optimization, this cell actually performs stratified cross validation and searches for hyperparameter that maximizes the macro F1 score. This step significantly improves performance compared to the baseline model. Once the optimization is complete, the cell prints the best macro F1 score and the corresponding hyperparameter is found by the optuner. Final light GBM model training and evaluation. Using optimized hyperparameters, I now train the final light GBM model on the full training dataset. Here I evaluate the final light GBM model on unseen test data. I again report macro, micro matrices along with the classification report. After the classification report, a confusion matrix has been used. It is used to provide a class-wise view of model performance and highlights common misclassification patterns. Here is one of the important step, which is the feature important analysis. This plot shows feature importance for light GBM model. It helps identify which environmental features contribute the most to the prediction. We can also see the elevation related and the distance based features play a major role. So here we'll be training an alternative classification model on the same dataset and compare its performance against the tuned light GBM model. So we'll compare the macro and micro F1 scores, training time, model behavior. The random forest is chosen because as a strong assembled baseline. To compare models, I have trained a random forest classifier using the same training dataset. This ensures a fair comparison between the models. This cell evaluates the random forest model using the same metrics as light GBM. They consistently allows a direct comparison of the performance. So after training the dataset the both the models, here's the comparison. From the comparison, random forest has achieved higher macro and micro F1 scores, indicating better predictive performance. However, light GBM trains faster, is more scalable, which is important for large data sets. In the end, I'll be concluding by saying that the project shows the feature engineering and tuning significantly improves performance, and that model choice depends on both accuracy and efficiency. The comparison highlights a trade-off between the predictive performance and computational efficiency. While random forest performed better in terms of F1 score, LightGBM remains a strong and efficient alternative for large datasets. Thank you.